Prof. Pedro Jugo, who has been up since, I think it's 2 a.m. It was 2 a.m. in the morning. So thank you for joining us that early and staying on. I trust you are still awake. May you please share your screen while I introduce your talk, which is Understanding PGE Mineralization in the Bushveld from the Flatreef perspective, implications for the entire Bushveld igneous complex. Thank you. You may share your screen. Oh, there we go. Thank you.
Okay, so just let me do one thing here. Good afternoon for all of you. It's now 7:45 for me, and my worst fear was to fall asleep through this series of talks, but the talks have been fantastic. So thank you all. I learned a lot. What I want to do today is showcase the progress that my research group has done on the Flatreef. And then what I think could be of interest to other people as well is to flip the tables in a sense and look back at the rest of the Bushveld with that perspective on the Flatreef. And as I mentioned in the abstract, one of the things I would like to do is to propose that we need to come together as a group of academics and industry people in trying to develop some reference sections that will help us move forward. One of the things that I found interesting, for example, today through the presentations and the talks and the questions afterwards, Nicole mentioned the point of the variations laterally in this the western limb, and Gordon also mentioned about these different phases. And I think it is very tempting to extrapolate to the whole Bushveld based on a study on one corner, and I think maybe we can gain a lot if we develop similar parallel studies that do multivariable approaches to different things. So one of the things I want to do is to showcase what we had done on the Flatreef, not necessarily as an example, but it's just what I'm more familiar. So again, my intention is to make a case for the need of several detailed reference sections. There's some examples which are very good and actually inform how we approach the problem for the Flatreef, and I'm highlighting one, Keir-Sage, which is from Maya's research group. This is from the Union section, and I'll argue that more things like these could be very useful. So I would like to acknowledge again, this is a collaboration, it's a team. This is our research team, Laurentian, Charlotte, Evan, Cedric, Michael, and Jan. Charlotte and Michael is part of this collaboration we have to the University of Limpopo. Evan and Cedric were part also of that collaboration. They actually went and taught for a term in Limpopo. And it's also a lot of group collaborators. Matt Liborn is our geochemistry help. Danny has a wealth of information on Bushveld and the Flatreef in general. And Jacob and Henrik help us with some of the details of analysis. And all this has been sponsored in a partnership with the Natural Science and Engineering Research Council of Canada in partnership with Ivan Plants. And a lot of the students have been funded by these two organizations in Canada. So why do we want to do these? Why do we want to speak about these things? And everybody would agree there has been a continuous and steady progress on knowledge about Bushveld in terms of the petrogenesis of the Bushveld and in terms of the origin of the PGEs. And these have resulted actually in multiple hypotheses for PGE mineralization in the Merensky and the UG2, but it has been somehow difficult to establish testable hypotheses that allow us to actually, instead of increasing the number of hypotheses, to narrow it down to something that is more manageable. And as somebody who's relatively new to work in the Bushveld, you know, from the point of view of petrology, Bushveld is from the point of view of the Mecca of petrology. There's so much happening in there. If we can understand the Bushveld very well, we could probably understand many deposits elsewhere. And as Wolf mentioned early in the morning, the reality is that even though years ago it was this conception that we knew Bushveld very well, the fact is that the more we look, the less we learn. The more we learn, but the less sure we are about what's going on. And I think, and I would argue that part of the problem is the variability between limbs and among sectors within each limb. And I think there is an opportunity to turn these from a problem that is mostly a problem from the point of view of mining operations, and as Nicole was mentioning, to the point of view of what can we gain in terms of petrological information. Because I think if we can compare what is different and what is similar across these facies variations, that may lead to us trying to figure out which hypotheses stand and which are not going to. So I would like to do three things. I want to very quickly summarize some of our recent progress on the northern limb from the establish that framework of the Flatreef perspective. And then I'm going to compare some of those with examples from the eastern and western limb. And I want to start pointing out subtle differences in the eastern and western limb that has been captured, and some similarities between sectors in the eastern limb and northern limb that are hinted by some data. And that's what I think there's an opportunity. And again, I want to emphasize two aspects. I want to showcase the supporting evidence for a Merensky Unit correlative in the northern limb, and highlight the similarities between northern limb and eastern limb. So the highlight of the work we had completed, Cedric Mayer did the strontium isotopes, Evan Keir-Sage did sulfur isotopes and whole rock trace and major elements. Charlotte Mkhonto did sulfide mineral chemistry. Michael Langer, who's ongoing, started working on mineral chemistry. So I'm just going to try to capture these in 3 or 4 slides per project, which is not too much. And most of these is going to come in that special volume on the Flatreef. So bear with me. So part 1 of 4, strontium isotopes done by Cedric Mayer. Quick background, because there's a mixed variety of people in this audience, as we saw. This is one of the early papers, Kruger and Marsh and Science or Nature, 1982, and the Rosenberg. And what I highlighted here in blue is the Merensky Unit, and these are the strontium isotopes. The scale here is not really, the details are not relevant. The main issue for the strontium isotopes, we're using them as a tracer. So what this always is this shift. It goes from certain values, it enters the Merensky Unit, and then the values go high and then kind of become flat and constant. So this transition has been documented elsewhere, and in fact is considered one marker of the Merensky Unit. So in a quick way, the nutshell of the hypothesis that we wanted to test was, okay, if the Merensky Unit of the equivalent is exists in the northern limb, then that strontium isotope feature should appear. And if there's no feature, but the strontium isotopes are magmatic, then one could say it's unlikely that this was Merensky related. And if Merensky-like features appear, I would argue that it's one of the best lines of evidence for a correlation between the two. And again, at the beginning of this presentation, what we want to emphasize is the correlation based on these features. And later on, I will try to argue about some petrogenetic implications of these. So as Danny mentioned, there are huge variations as you go across. When you go towards the eastern side is when you see most of the interaction with the local contour rocks, which in my opinion is what had progress previously, because the level of contamination with local contour rocks makes really difficult to see anything. So we wanted to look at, okay, can we establish something that is close to the end member? Where do we go? And we went to, well, be the deep extension of the Flatreef. And in this drill hole, core logging and our own visual inspection showed that there were very little visual evidence of assimilation. So if we were to see any strontium isotopic anomalies, this would be the place that they would show. So let's go to the results. So on the left, I have the reference slide that I showed you previously from Kruger and Marsh. And these are the results that we found. It is the Merensky unit in that equivalent stratigraphic revision that Danny presented in 2009. As you can see, the destruction isotopes are pretty much flat in the footwall units. And then you had the sharp increase. And then there is a decrease, and they go to relatively high values, not as high as low, sorry, relatively low values, not as low as below the Merensky unit, but they don't go up. It's not, you compare to the reference that I have here for Kruger, they go high and they remain high. We have this increase, and then we have certain decrease, which is going to be important later on. So check mark 1. We can see this characteristic. I will be hesitant to call this a signature, but it's as close as you can get to a signature of a stratigraphic correlation. Then the step 2, which were done simultaneously, was to look at this, a typo here, is to look at the sulfur isotopes and whole rock geochemistry, and that's the work that Evan did. And again, a bit of background. Somebody alluded to this before. This is a summary that Magalhaes student and Sarah Paris-Tondorland did. And they look at 2 different types of sulfur isotopes. We only look at this delta 3 for sulfur. And the main thing I want to emphasize is this range to roughly -2 to close to +4. And these are samples from many places in the Bushveld, in the Rustenburg layer suite related to the Merensky. The black dots are actually in part of the northern limb. So again, trying to simplify things to the core, the hypothesis is fairly simple. The hypothesis is if PGE mineralization is not caused or not triggered by a simulation local contour rock, then the sulfur isotopic value should match what is known for the Rustenburg layer suite. And so if it's less than +4 per mil, then no local cross addition, at least to the sulfides. And as has been shown before, the PGMs are closely related to the sulfides. So we assume that PGE mineralization, if you track the sulfides, you track the PGEs. And values higher than +4 will reveal a clear indication of sulfur contribution from the local contour rocks. And it's important to establish a local contour rock, because one of the things that have been established before is that the sulfur signatures are non-mantle. So there was some level of contamination somewhere, but what we try to test is that contamination common to what happens elsewhere in Bushveld? If you go in the eastern and western limb, you have thousands of meters of rocks underneath the Merensky unit. So there's no local contour rock contamination. It must have happened at depth. So these are the results. Danny had a slides briefly comparing these. I will have another one later on. So what I have here is the stratigraphy on that plot. Also a bit of the chemistry that we had in loss of ignition, which is actually this curve in here. And then what you see in here, especially in this region, the red dots and the circles are the sulfur isotopes. This orange box is the range of values that we got from the rest of the Bushveld, and highlighted in blue, the Merensky unit. And as you can see, as you go deeper and you get into the footwall assimilation zone, both the loss of ignition and the sulfur isotopes start to increase. So anything on this range higher than 5 is arguable that this contribution from the local contour rock. But where you have the mineralization, where you had the Merensky unit, is well within the range for the Rustenburg layer suite elsewhere. Step number 3, okay, can we look closer at the sulfides themselves, the sulfide chemistry? And this is the work that Charlotte did. She just defended in January this year. And a bit of background, there's nothing exactly compared to what Charlotte did, but this is an idea that helps to kind of drive the methodology. This is from a work of Charlie Duran and Sarah J. Barnes. And summarizing this figure, what you have here is 2 element ratios, cobalt, antimony, and selenium and arsenic in pyrite. And what you can see is that these ratios can be used to distinguish between different types of ore deposits, in this case, nickel copper PGE versus porphyries and so on. Of course, pyrite is not abundant in Rustenburg, but the question was, can we do the same using different sulfides? We had some confidence that we would see something, and that's how we approach. So what we saw before, as I showed you, is that the strontium, the sulfur isotope, it was the degradation in the sulfur isotopes from close proximity to the local country rock to things that approach or are within the range of the Rosenberg ledger suite. And the question was, okay, can we see some of these? Is there a record of these also in the trace elements in the sulfides? And there was also another piece of information that was useful. When we replotted the whole radiochemistry that we had from Ivanplatz for that particular drill hole, we saw that there were apparently two distinct populations. One that we started calling initially a high sulfur to nickel, there's a sulfur here, nickel on the side, and one that was relatively low sulfur to nickel, and something that seemed to be somehow intermediate, which we just labeled intermediate. There was something interesting too. There was a straight relationship with the stratigraphy. The ones that were higher sulfur, as you can see in here, were lower in the stratigraphy, which would be consistent with additional sulfur from the local country rock. So we generated a lot of different data for these. I'm just summarizing in two, because I want to make this relatively short. And one of the things that we saw was selenium was the most useful discriminant. You can see that higher in the stratigraphy, you have higher selenium, both in chalcopyrite and in pyrrhotite. The same thing happened with pentlandite. All of them had higher selenium. And the ones that were related to the footwall assimilation had lower selenium. We also saw, which is interesting because it was something we did not expect, that the cobalt content, particularly in pentlandite and in pyrrhotite, was higher as you were closer to the footwall. But you see somehow a mixing line. The ones that are high in the stratigraphy and with sulfur isotopes that are magmatic, essentially, having high selenium, relatively low cobalt. So keep that in mind. So what is the summary so far based on these three different lines of evidence? That we have two distinct lines of evidence supporting this interpretation of a match with characteristics to the Merensky unit, the strontium isotopes and the sulfur isotopes. And we have one line of evidence from the sulfide trace element chemistry showing that we can differentiate between the influence of local country rock assimilation in the trace element of the sulfides themselves. In addition, deep into the footwall assimilation zone, which makes it somehow problematic, there were intersections of chromitite seams, which were interpreted to be the UG2. So we use the same approach. Okay, if that is a UG2, can we extract any information from the chromatites that we can test to see if they match the characteristics of the UG2? And this is as a summary, the work of Nalder et al. In 2012. There was another paper before 2009. And it's in essence, what they will show here is that in the magnesium chromium space, the lower group chromatites plot on this upper right corner. And as you go, this is interesting because the stratigraphy is inverted. This is the LG going to the MG. And as you go higher in the stratigraphy, there is a trend going this way, which we call the trend, they call the trend B. And within the distinct LG groups or the MG groups, there were some trends that they call the trends A. And what they have here in black is a variable UG2 samples are from the western limb, from the southern part of the western limb. So we decided, okay, let's go to this slide. If that chromatite seams we call the UG2 equivalent, the UG2E for make comparisons easy, is a correlative to the UG2, then do those fields match? Just a little view of that. So here we have the main mineralization. You can see here these are the PGE grades. And as you go deeper in the stratigraphy, then eventually you intersect these, you see the chromium content, you intersect these massive chromatites in whole rock chemistry. When you look at the core, the intersection starts maybe from here all the way to here. But as you can see, there are only some patches that are massive. This patch here, for example, another patch in here, and another patch in there. And otherwise, although there's a lot of chromite, there's a lot of interaction with silicates. So that's, as I'm going to show you in a second, that makes this a bit difficult to envision. So that's a compilation that he did. In addition to the data that was presented by Naldred, we had all these LG groups and MG groups, and the UG and UG3. For simplicity, I'm going to remove that, and I'm going to show you only the UG2 compilation. Interestingly, through this work, Westler et al. Published some work in 2018, and we noticed that some of the data was available and useful. This data from the eastern limb for Enkwe is shown only as a field because the numerical data was not included in that paper, and the data for this Kuseleka is shown in this gray. So one of the things that's going to come back later is that there's a bit of a distinction in the fields between the eastern limb and the western limb. So we had Tony sent to us years ago that variable reference suite that he had. So we analyzed those, and spot on, they match what they recorded in the paper. We did this mostly for calibration. And then here's the data for the UG2 equivalent. And it's a bit of bad news in the sense that even though there is a bit of a match, especially with the ones on the eastern limb, there is a strange trend that is going downwards. No change in the chromium number, a continuous decrease in the magnesium number. And it was a puzzle. And we thought, well, this is not good news. How much emphasis do we put into the ones that seem to be a correlation and the ones that don't have a correlation? And that's when we decided to look closely at the chromatite seam and pay attention to the model proportions, which is what we're showing you here. So here what we have is the model proportions and the magnesium number. Of course, when you take your typical UG2 chromatite, it's massive. It's typically more than 80% chromite in the mode. And what we found is that in the UG2E, in the sections that preserve these massive proportions of chromite, there is a match. And as you start increasing interaction with silicates, there is a decrease in the magnesium number. Also, we decided to send some of these samples to establish the ferric iron content. And then we realized also that not only you get a decrease in magnesium content, but you have an increase in the iron content. And therefore, based on that, we added a trend C to those two trends that the Naldred are all established. And we argued in the case of the UG2E, what we see here is the effect of local contamination. So in the areas that are massive, you preserve the characteristics of the UG2. If you talk to Steve about this trapped liquid effect, I would argue that the trapped liquid effect is going to be the same if you have roughly the same proportion of chromite, and it seems to be a cutoff around 80% or higher, which would you preserve mostly the primary signature of the chromatite. And if you have low, then it's more interaction. And an interesting implication of this is that if this is indeed, as we argue, the effect of local contamination, then it means that the massive areas on the chromatite had to be formed before there was significant amounts of assimilation, or were preserved before ionic exchange could happen. So I'm going to go back to, this is one of the slides that Danny had. And here we're comparing some of those results. So we have here in blue, the sulfur isotopes, and we have in red, the strontium isotopes. And we add in here what I show you from the work of Charlotte in terms of these are the ones that have sulfides are distinct from the ones that had local cross contamination. And here are the PGE grades. And what else can we learn from these? So the summary of these is that I think there's good evidence for both Merensky Reef and UG2 correlations in the northern limb. And now what is, I think, probably the most value for the rest of the crowd is comparisons to the eastern and western limbs. So this is the reference example that I mentioned. This is the work of Keir-Sage et al. And what I think we should try to strive for, and probably I'm going to try some suggestions at the end. I would argue there's a lot of value in having multi-parameter information from the same locality. Here you have the strontium isotopes. There's the anorthite content in plioclase. There's the iron content you can see in here, so in plioclase. There's neodymium isotopes, and there's trace elements, cerium and samarium. So we took this page for our work, and here you have what we have, for example, in there is again, the strontium isotopes. Now we have the grades in here. We have also, we can see the cerium, samarium anomalies increasing right before you get to the Merensky unit. We see it is an increase in European, relative European anomalies in the whole rock. This needs to be refined to plioclase. We see the same. Now, I think what I would like to do is to emphasize some of the differences and infer that, or try to make a case that looking at these differences may give us a clue of where to go next. So these are comparison on our data in brown and the data from Young et al., which is also part of the Myers group in 2013. So you can see they begin exactly the same. The change in the strontium signatures is the same. There's a bit of a gap on data in there because we did our study with more resolution, maybe because we were paranoid we will miss the marker. And but we don't see that continuous increase. Instead, we see this increase and then that decrease. So the question is, okay, does it mean that the northern limb is different than the rest of the Bushveld? And here is a figure, it's a compilation. This is a work of Seabrook in 2005, and 6 different localities in the Bushveld, 4 in the western limb, 2 in the eastern limb, and compared to what we have. So we see this increase and then a decrease in the strontium isotope signatures. In the western limb, in the Union section, in the Rustenburg section, and the Brits, you can see roughly the same. It goes up and then pretty much flat, goes up and then pretty much flat. But when you go to the eastern limb, some things seem to be different. In some places on the western limb, you see the same. Here you see, for example, that it seems to be a slight decrease as you move upwards. Especially in Attock, you can see that it starts to go up and then it goes down somehow in a similar fashion to where we are. And interestingly, when you look at these in the map, and you see that Attock is on the uppermost part of the eastern limb, and in a sense, in terms of location, the closest of all the data compilation that we can have to Tushbrook. We have done also some other comparisons. This is something that is actually Charlotte did after defending her thesis. It's a bit of a cumbersome, there's too many lithologies in here, so I'm just going to highlight to you what is important. These dots in black is the data from Hutchinson 2005 on the Merensky Reef. These pinks are data that we capture on samples that we collect in the Merensky Reef on the Impala platinum mines. These red triangles is from the shaft 1 that Danny mentioned. And this red, this is M2 on the reference hole that we have. Now, this is ruthenium in pentlandite against selenium. This is palladium pentlandite against selenium. And what I would argue is that the PGE, palladium in pentlandite content that we see, and ruthenium content in pentlandite that we see, is a pretty good match with what we see in the Merensky reference sections, for which there's not much data. So I think more data needs to be shown in here. So again, doing that comparison, I want to emphasize the key differences in here. Again, I mentioned this before, some difference between the western limb and the eastern limb. And again, you go back to the map, then you can see that these ones, which seem to be more consistent with what we see in the UU2 equivalent, come from the eastern limb. and the ones on the western limb are the ones that are distinct. So there seems to be some subtle differences between the eastern limb and the western limb. And I would argue that if we do profile sections of this kind on the eastern limb, we can probably find interlimb and interlimb variations. So one of the things that I would like to see, and this is not something that I would love to do this, but I think this has to be a collaborative work, is if we can develop reference sections on different places in the Bushveld. I highlight some in red. This doesn't not necessarily have to be the ones to be chosen. I think this needs to be formed by the kind of data that Ian showed this morning in terms of geophysical anomalies, by the kind of information Nicole showed also in terms of the variations in the Marikana mine, and some of the variations that Gordon was talking about, other places in which we see this. So in summary, because I'm just like running a bit short, is we do see a correlation with some of the topmost part of the percritical zone in the northern limb compared to the eastern and western limbs. I agree with Danny that we have to be cautious about these because there's some things that we cannot explain. More than anything, the contrast in the thickness of the PGE mineralization between the limbs. And I would argue that the available data, which is not conclusive, points towards some intra and interlimb variations that I think we can learn a lot if this could be quantified much better. And also point to some similarities between the northern limb, or at least part of the northern limbs, and part of the eastern limb. And I would argue also that we need to look at these at different scales of resolution. Some studies that we'll try to use for comparison, for example, with the strontium isotopes, we're looking at the entire Bushveld igneous complex, and then the resolution at the scale that we needed is a bit lacking. There were some gaps, so we need to scale according to what we need to do. I think I make a convincing case. And there's a lot of value in multivariable reference sections in which you can compare simultaneously variations on the same parameter, and especially in terms of PGE grades and whole radiochemistry and different isotopes. And this is mostly something that I would like to point to you as a point of discussion within the community, whether it is a way to have a centralized data repository. One of the previous slides, I have it in the text, but I didn't mention the GeoRock, which is a compilation of publications. And in my experience, in recent experience actually, I find that it's a lot of data that has been completed in DSc thesis and MSc thesis that is not captured, that is not available unless you spend a lot of time digging into. There is a lot of information that mine geologists have that is extremely valuable, that is not captured, and is essentially captured as an oral tradition of people that come work in the mining industry. But I think we need to make a better effort to capture some of that, which is extremely valuable, and have it in peer review literature and safe for future generations. So I thank you all for your attention and your patience, and I'm open for questions. And I just want to acknowledge my sponsors and my affiliations in here. Thanks very much.
Great, thank you. Thanks again for that very interesting talk and the research that you are doing. And thanks again for staying up and waking up so early rather. And yeah, staying on for the whole day. So much appreciated. And look, that last point about a central repository, that's a discussion on its own. A lot of people have ideas, and I'm sure some of the participants have as well. But what I'll do, I'll open up just for one question. I see, Steve, you've got your hand up.
Yeah, hi Pedro, great talk, really interesting. Just one point about your chromite trend, your vertical MgO with chrome. The possible thing that might be going on there is you might be seeing subsolidus equilibration between the chromite and the silicates, and that kicks in. That's the sort of trend you get for rocks with sort of tens of % chromite in them, where that essentially the chrome aluminium ratio and the chromite can't change, but it's equilibrating with different proportions of mafic silicates, and that will give you that trend. So you might not actually need you might not need anything more exotic than that to explain it.
Correct. I agree. The coupled to that though is the increase in the ferric iron content, and if you had a closed system in which the only thing you had going on was equilibration with an increasingly larger proportion of silicate melt, then the trend would be more towards the higher chromium number, which is what you see in the dispersion of the array data. If you look at the array data, you see a dispersion towards lower magnesium number and higher chromium number. It's something that Wechsler has shown clearly, and we see that also on the margin of the vein. So anything that has a magnesium number lower than 0.4 seems to be related to these chromides being within the silicate matrix, which will be totally consistent with what you're saying of subsolidus reequilibration. So the trend that we see vertically, I think, is a combination of two things. Obviously, subsolidus reequilibration, but with a silicate melt that has seen addition of contour rock that increase the ferric iron content.
Okay, sure, yeah. Well, something to look for then, if you are seeing a trap liquid reaction, the other thing you should see is an increase in titanium. That's the characteristic of that trend.
Yes, we need to look into that for sure.
All right, sorry, I'll just let the last question, Jock.
Hello? I think to have lost the audio.
There we go, yeah. Pedro, one of your early slides, you've used the Kruger-Marsh strontium plot and sort of used as a characteristic of the Merensky that kick in strontium ratios. In one of your last slides, you were sort of talking about getting a profile and ad hoc to compare and so on. There are two publications on a detailed strontium. Chris Lee and Alan Butcher published the strontium ratios through the section at ATOC. And I used those samples and we did some lead isotope ratios. And in both the strontium and the lead, it is very, very clear that the inflection in the strontium ratios occurs well above the Merensky reef, above the Merensky reef at ATOC. In other words, it's in the Bastard unit, not. So you don't get it, there's no transition slowly changing across the Merensky. The Merensky is exactly the same as the upper critical zone. And the inflection comes above that. Yeah,
okay. Could you perhaps type in the comments that reference so I can capture it? And that's a very interesting point. We do see that inflection happens before the Bastard, as I show in here. The inflection happens somewhere in between. So there's some differences, and that's what I would like to look in more detail.
Yep.
Because the one thing I'm cautious at this point is to try to establish a cause-effect relationship between the strontium isotopes and the mineralization. Since I had this slide in here, one of the things I want to mention, for example, is that the grays kick in when you start having an increase in the strontium isotopes, but there's significant PGE content below. So this, if anything is related to this increase in the strontium isotopes, essentially is bringing the grades by a factor of 10, which is not a lot. So this is what I want to look in more detail. So thank you for that comment.
Sure, because the Kruger-Marsh stuff was mostly sections in the Western Bushveld.
Correct.
Whereas the ATOC stuff, it shows, from the mine, the kick is well above where the grade is. Okay.
Thanks.
Wonderful, great. Thank you very much. Like I said earlier, we'll leave the conference going on in case there are further discussions. So thanks again, Pedro, for staying on for so long and a very informative presentation. Thank you very much. I'm just going to share the results of the last poll, which was about the connection